I would ask the next speaker, who is Rabindra Mohapatra, to give his talk on the unified theories of neutrinos and dark matter.
Thank you.
Hello,
Thank you, how are you?
Nice to see you.
Nice to see you, right? Let me just try to...
Yes, I already put you as co-host.
Can you put me as co-host?
It's already done. Hi.
So you can share your screen, I guess.
Yeah.
Yeah, you can share the screen. Yes.
Can you see it?
Not yet. Now it's okay.
Yes.
Okay. Should I start?
Yeah, I'll warn you at 13 minutes.
Okay, thank you. First, I would like to thank the organizers and Hore Alfaro for inviting me to give this talk. So what I will talk about is something that we just did within the last year and is still ongoing work. We are thinking about it. So this is in some sense, there is only one publication and hopefully you will give comments so that we can improve the rest of the publications on this thing. So the title of the talk is Minimal B minus L Theory of Neutrino Mass and Dark Matter. As you know, dark matter is one of the major puzzles of standard model. Let me just see if I can change my... Okay. It's a major mystery of particle physics and cosmology is the nature of dark matter. And of course, understanding dark matter will provide a new window to BSM physics. So the point of view I'm taking is that there are already a lot of models for dark matter, but it's still important to pursue as many scenarios as possible and pursue them experimentally possible. So here is a current theory landscape from the Cosmic Vision report, which tells you what kind of dark matters are there. There are hidden sector dark matter, thermal wind dark matter, asymmetric dark matter, and also all kinds of mass ranges going all the way from really, really tiny in this end to really heavy, including massive black holes. Okay. So what I like to do is first give you an experimental landscape, which tells you that there is a WIMP search going on for a long time, and we haven't seen any evidence for dark matter. And here are the cross-section limits for the spin-independent dark matter nucleon cross-section. And you can see that it's going really low and low. Let me see, it suddenly went down for some reason. Should I put the slides or what? Is it okay? Everybody can see it?
Yes.
Okay. We can see it. If you like, you can widen it, but now we can see the whole screen.
Can you see it? Okay, great.
You can see the x-axis.
Can you hear me also?
Yes, we can.
Okay. So the point on this slide is that you can see that the search for the dark matter has gone to very precise values of cross-section, and it's now almost reaching something called neutrino floor, so that at some point it will be impossible to distinguish between the neutrino signal and the dark matter signal, and that will be kind of sad for... So that's the story of the WIMP dark matter. So what I want to do today is to add another candidate which avoids these bounds and also unifies the dark matter with the neutrino mass. Okay. So this is motivated by a neutrino mass model, which is an extension of the standard model by a simple E1 symmetry, and then you get the extension. And the basic framework is simply that you take the standard model and add 3 right-handed neutrinos, and this is quite well known that it leads to an anomaly-free B minus L symmetry. And of course, the breaking of B minus L leads to seesaw mechanism, as Jose just described in his talk. So what you want to do is just take the standard model and then extend it by U1 B minus L. That's the model. And I will show you that the Lagrangian for this model just fits in one slide. And it's a very simple minimal extension. Now, of course, we all know that the breaking of B minus L gives rise to seesaw. And this is the seesaw formula where VVL is the breaking of the B minus L symmetry. Okay. But before I get into the model, I just wanted to distinguish. In the literature, there are 2 classes of B minus L models. And the first one is where the B minus L depends on what the middle U1 of the previous slide is. So if the middle U1 is U1 I3R, then what happens is that the electric charge becomes a formula like I3L plus I3R plus B minus L over 2. And that has very strong implications. It implies that the electric charge is related to all the three gauge couplings in this way. So that means there is a lower bound on the GBL. You can't make GBL very small. And that's a limitation on this class of models. But of course, they're attractive in the sense that they are part of the left-right models, as certain models and stuff like that. So what I want to talk about is the second kind of B-cell, where the middle E1 of the extension is E1 hypercharge. Okay? Then the B-cell does not contribute to electric charge, and the electric charge formula is simply I3L plus Y/2. But its breaking of B-cell still gives seesaw and hence explains small neutrino mass. And in this case, of course, since B-cell gas coupling does not contribute to the electric charge formula, what you have is an arbitrarily small GBL, and that helps in making something in this model a dark matter, which I will come to right now. So the minimal version of this model, therefore, is very simple. It is SU2 plus U1 of the standard model, then U1 B minus L, and the B minus L gas coupling is very small, and we will see what are the rest of the constraints on the model. So the minimal version of this model, we claim, explains both neutrino mass and dark matter. So let's now go to a little bit of the details. I have to run because of the time, but here is the, hopefully this is a little bit clear. So what you have is the standard model plus 3 right-handed neutrinos. So you have, for each generation, you have these two doublets, singlets, and the right-handed neutrino. And here is the gauge group, and there are 2 Higgs bosons. That's it, the Higgs doublet of the standard model, which we are all familiar with. And the Higgs has been discovered, so this is pretty much well confirmed of this part. And the additional fact is that you have a Higgs singlet of the standard model, which breaks the B-L symmetry, and that Higgs singlet wave is much larger than V, which is sort of the common assumption. Now, of course, once you know that this gives the seesaw, as I already said before. So the Lagrangian of this model is, as I said, it fits into one slide, which is that you have a gauge sector, you have a kinetic sector, you have a Yukawa sector, and the potential. And the key things for us is the Yukawa sector, which is this one, the quark part, the lepton part, and the nu part. So the second line is the nu part, right-handed neutrino, and with the new Higgs, and the right-handed neutrino with the standard model Higgs doublet. And the potential is simply given by this very simple formula. There is nothing else in the model. There are only 2 Higgs doublets and the right-handed neutrino. The last 2 terms, of course, of the Yukawa coupling gives you the seesaw, as I just described. So what is the dark matter in this model? Well, the dark matter turns out to be the Higgs that breaks the B-L. And that's kind of unusual, as I will discuss, and how we make it a dark matter is the interesting part of the talk, I think, at least for us. So if you have a delta field that gets a wave, then what you will write in working out your Lagrangian is a delta equal to real part, sigma, imaginary part, and the wave. Now, of course, we know that the imaginary part gets absorbed into the longitudinal mode of the B-L gauge boson GBL, whereas sigma is a physical field. So this, in the unitary gauge, this is physical field, and our claim is that sigma can be a dark matter candidate. And this is highly non-trivial because we know that the sigma couples to B-L gauge boson, it couples to the right-handed neutrino, and in general, it is unstable. So how can an unstable particle be a dark matter? Well, if there is a parameter range in the theory where the dark matter lifetime is really long, then it's fine. It can still be a dark matter. And there is, of course, many explorations of the idea that the dark matter may be unstable, very weakly unstable. Okay. So the stability of the dark matter is therefore a very important question. And what, of course, is well known in the literature is that the dark matter eventually often decays and gives rise to gamma rays. And there are constraints on this gamma ray spectrum from the Fermi-Lat and many other experiments that are known, and they're all summarized in many nice reviews. But the bottom line is that whatever the dark matter is must have a lifetime which is much longer than the age of the universe, and is about 10 to the 25 seconds or 26 seconds. And the question is, in this model, can we satisfy these constraints? So this is the key slide, actually. So in other words, the sigma of the B-L is the dark matter, and it better be that there is some range of the parameters of the theory where the sigma lifetime is much bigger than 10 to the 25 seconds. Can we do that? So let's just look at the sigma decays in this model. Well, sigma can decay in many ways. There are a couple of hand-drawn graphs here. So you can see that sigma couples to 2 GBLs, and the GBLs can, of course, go to, because these are B-L, they can all go to the standard model fermions here. And sigma also connects to NN, the two right-handed neutrinos, and that also again eventually decays to standard model fermions. So therefore, these are the two main contributions that we have to worry about. It turns out that for the range of parameters we choose, this one is the right-handed neutrino contribution to the decay is actually very, very small. So therefore, the main contribution we have to worry about is the GBL contribution, and what you find is that you write down the decay width, and you see that this is a very high power of GBL, and this is small, as I said, so this is easily satisfied. But if you look at this formula, you see that it prefers low GBL coupling and the light dark matter. So that's the two key features. The dark matter mass must be small, and well, not must be, but at least convenient range is this is small mass dark matter, and this is low GBL coupling. So if you look at that formula, what you find is that the lifetime constant of the GBL is something like less than 10 to the minus 7.5 over these factors here. Now that is extremely small, and of course that's why the first class of B minus L models cannot satisfy this constraint at all, because there is a lower bound on them, but the second class does, and there you see that this is very easily satisfied. So what we have to do is look at other constraints from this. Can we generate enough relic density with such a weak coupling or not? Okay, so there is just one other. So here is a typical benchmark set of parameters for the model. The dark matter mass, there are several ranges, but one range I will focus today due to lack of time is the MeV to GeV range. The GBL mass is about 10 MeV to 100 GeV, and the GBL coupling is extremely small, 10 to the minus 7 to 10 to the minus 4. As you can see, it can be larger if the sigma mass is small, and the right-handed neutrino mass is a TeV, and this is VBL is 10 to the 6 GeV. Okay. So I'm not doing any naturalness, or I'm not worried about that. I'm simply trying to find out if there is a range of parameters in the theory where this plays the role of a dark matter. And if this is the theory, then of course we'll have to look at naturalness issues. There is just one other constant on the model. If you remember, there is a coupling in the Higgs potential that I just showed, which is two Higgs standard model Higgs doublets and the new Higgs multiplied term. So what we do is we set this to 0. This is not so unnatural, because if you have a supersymmetric theory, that is automatically 0 and only induced at one loop. So at one loop, what you have is a gauge-induced term is not present. The only term that is present is the right-handed neutrino mediator term, and you evaluate it, and for the range of parameters we are talking about, this is an extremely small number, and the lifetime requirement is satisfied. Okay. So then the question is, how do you satisfy the relic density constraint? Because it's such a small coupling, it's counterintuitive that you can satisfy the relic density constraint. So let me just review the ordinary WIMP scenario. If you look at the WIMP scenario, then what we have is a thermal freeze out, and the typically dark matter is in equilibrium for some large high temperatures, and then as the temperature goes down, the dark matter pairs freezes, annihilates to standard model fermions and freezes out, and then it becomes dark matter. But since our parameter couplings are small due to lifetime constraint, it's not satisfying the WIMP kind of scenario. So what we have is something called freeze-in scenario, which was suggested around 2010. And the dark matter was not in equilibrium with standard model in the early universe, but it was with GBL, which is weakly interacts with the dark matter was. So in other words, in the very early universe, the standard model fermions were in equilibrium with the GBL, but GBL had some coupling to dark matter, and that is what generates the, so in other words, you have GBL scattering giving rise to sigma, and that produces the dark matter relic density over time. So the constraints that you have to satisfy for that are all consistent with the long lifetime. So these are the constraints on the GBL. So if it is within this limit, then you have got everything satisfied and you have the right relic density. So I guess I'm running close to my end of time.
Yes,
I don't know how much time I have.
You're close to it.
Close, pretty close. Okay. So there are several other things you have to worry about. So we did worry about everything, and it's all in the paper that is published. And what happens is this is the typical way that the dark matter relic density is satisfied. You have the freeze-in scenario, this black line, this is the usual freeze-out WIMP type of model. So we are looking at this kind of model. Okay. And there is only one value of the GBL, where the relic density constant is satisfied, which is 10 to the minus 6 in terms of GBL coupling, MBL over GeV and MBL over sigma. So once we are in this range, then everything is okay. So we have a dark matter which is long-lived, and also its relic density can be generated. So this is a really new kind of dark matter. And here is this picture, which I cannot explain everything in this short time, that this picture essentially captures all the constraints of the model. The lifetime constraint, the relic density constraint, the equilibrium constraints, and all those kind of things. And so please look at the slides to get a picture of this kind of thing. So it turns out that in this class of models, there is a lower bound of the GBL mass, which is something like 227 GeV, M sigma over GeV. So for something like an MEV, it's a very low mass GBL, which is completely consistent with what we know because the GBL coupling is very small. Okay, so let's just focus on this mass range. There is really another mass range, which is the PeV scale dark matter, which I'm not going to focus on here. That's all possible within this model. So there are a couple of other constraints you have to worry about. There is something from supernova, because if you have a particle which is less than 100 MeV, it can be produced in the supernova. And it turns out those constraints are also quite well satisfied for the range of parameters we're talking about. And then there is a constraint from BBN, which is something like, this is a very complicated issue to discuss here, but roughly speaking, if GBL value is bigger than 10 to the minus 5, and MGBL bigger than 10 MeV, you satisfy the BBN constraint quite easily. And finally, just about the last 1 or 2 slides, this kind of models can be tested at LHC, but not the usual resonance search kind of LHC searches, but you have to look at something like low GBL range. And there is an experiment called Phasor Detector near the Atlas, which has been approved by CERN, where one can look for these kind of particles. Okay, so what you essentially do is you have a hadron PP collision, and that produces pion and eta, which decays to the GBL through pion going to gamma plus GBL. And then the GBL, because of this small coupling, it's a long-lived particle, so it gives us displaced vertices. And those displaced vertices is what can be looked for in the Phasor experiment, SHIP experiment, and other experiments being planned like LDMX and so on. So here is a picture which is very busy, but roughly what this tells you is what are the regions of the parameter. This is GBL and this is MGBL, and what are the parameter regions that can be explored at the LHC, and different experiments. This is LDMX, LHC, this is SHIP detector, this is the Phasor detector, and these red lines are the lines where the relic density constant is satisfied for the dark matter, and the dark matter values mass goes from 10 keV to 10 MeV. This is the range that can be tested. So this is the 10 MeV line, this is the 10 keV. So just one more slide and then I quit, which is that the direct detection is very easily, constraint is very easily satisfied, because the only way the sigma can scatter is to emit 2 GBL particles, which then interact with this one. But since the GBL coupling is so small, this cross-section is extremely small. So the rate is much too small for our GBL values, and it therefore satisfies the constraint for direct detection limit. So just to conclude, the takeaway lessons are that it is possible to construct a dark matter model which is extremely simple. Just take the standard model and extend it by U1B minus L, and then what you find is a dark Higgs, which is almost dark. In other words, it decays, but it's hardly visible. And the part of the parameter region of this model is testable at LHC. And the ideal setup to probe this is also, we are looking at this possibility that it can give some signals at Dune experiment in Fermilab. And there are other parameter ranges for the same model where you could have a PeV kind of dark matter. Okay, so I think I'm done. Thank you all. And thanking the organizers again for inviting me to give a talk.